Dr. Viswanathan has over 35 years of pharmaceutical industry and professional experience in USA in the fields of computational drug design, molecular modeling, and informatics. As the Vice President of Computational Chemistry and Informatics at Jubilant Biosys, he has led drug discovery and informatics projects and mentored research scientists supporting drug discovery, chemical database, and computational methods and tools development.
Hello.
Mr. Anbu is a computational chemist with nearly 3 years of industrial experience at Jubilant Biosys, Bengaluru. He has worked in various small molecule drug discovery projects using advanced computational tools to drive progress. Mr. Anbu holds an M.Pharm in pharmaceutical chemistry from Tamil Nadu, Dr. MGR Medical University. His M.Pharm project won the state-level first award from the Tamil Nadu Pharmacy Welfare Trust in Chennai. Currently, he works as an application scientist where he is involved in promoting and doing pre- and post-sales training on the computational chemistry software solutions marketing by Molecular Solutions. It's great to have you both, Dr. Viswanathan and Mr. Anbu here.
Hello. Can I share my screen?
Yes, yes, absolutely.
Yeah. Can you see my screen? Hello?
Yes, we can see it.
Okay, thank you. Yeah, I understand that I have about 1 hour time, both myself and Anbu included. And so I'll probably talk up for about half an hour and then take questions, Q&A for about 10 minutes, and then allow Anbu to do a demo for another 20 minutes. I hope this is okay. And this evening, I'm going to talk about free energy perturbation approach using a toolbox known as XFEB for accurate binding free energy predictions and the prediction of unbinding kinetics, that is residence time of ligands bound to drug targets. And actually, Raghu gave an introduction kind of speech to what I'm going to present. I'm going to present in some detail the recent developments in the structure-based drug design. The first is the central problem in drug discovery and the role of computational chemistry, how it evolved, and a brief on traditional SBDD approaches and the modern free energy perturbation approach theory and methodology. And I'll talk about a general drug design workflow and how XFEB toolbox is useful for FEB calculations for relative and absolute binding free energies. And then I'll talk about the Hamiltonian that is to be used in the XFEB toolbox, known as XFF. And I'm going to touch upon several diverse case studies on drug design using these tools. And then I'll talk about unbinding kinetics and prediction of residence time of ligands in protein. So what is the central problem in computational drug discovery? That it has to do with two things. That is designing drugs which are safe and effective. The efficacy of a drug depends on its binding affinity. So accurate prediction of binding affinity is the most important factor in drug design. In this talk, I'm not going to talk about the safety of the drug, which is also studied with computational models. And Raghu touched upon the kind of software tools that we need to ensure that the admin properties are under control for coming up with candidate drugs. So, as earlier described in the talk by Raghu, molecular dynamics is useful. However, binding affinity cannot be accurately predicted. MD is used to study the physical movements of molecules over time based on equations of motion. It allows you to visualize the binding process, study conformational changes, assess binding stability and affinity, identify key interactions, and it also is useful for data optimization. And there are several tools available in the public domain also. But the limitation is that MD does not include the framework for accurate binding affinity prediction that takes into account water thermodynamics and protein flexibility, for example. And predicting binding affinity of a designed drug is a challenge. So let us say that we have a protein to which two ligands A and B bind. So which of them binds better and by how much? Especially we need to make this determination when ligand A and ligand B are related. So docking and scoring methods are not accurate enough because they don't take into account all aspects of binding affinity prediction. And MD, as I mentioned, is not a complete solution. Now, I'm going to talk about this physics-based method. Now, in the era of AI, what is the relevance of the physics-based method? Actually, AI, as you all know, is dependent on the quality of the database, from which the AI model is derived. And you cannot have an infinite amount of experimental information to derive these AI models. You are very limited in terms of what you have in terms of experimental data. What free energy perturbation theory allows is that it allows you to uh, experimentally predict the binding affinities with an accuracy approaching, let us say, plus or minus 1 kilocalorie in terms of binding affinity. But the whole point is by improving the Hamiltonian that goes into these equations of FEP, it is possible to improve predictions considerably in the foreseeable future, and that is going on. I'll talk about it. So you can have a database, a computational database that allows you to develop AI models very accurately, and that is definitely going to come in future. So the FEP approach enables answers to two questions. Given two molecules, A and B, which have similarities, which molecule has greater binding affinity, and what is the difference in binding affinities? And what are the absolute binding affinities of A and B if A and B are dissimilar? Generally, the workflow for drug design varies from organization to organization, but let us take a generic case where you select a protein target, preferably with known exit structure, and preferably with a reference ligand bound. Obviously, we have these data are deposited in RCSB database, and what we can do is we can explore the chemical space to identify potential hits for this particular target. And Dr. Faisal already gave you a talk on how this chemical space can be explored to identify potential hits. And Raghu touched upon how XMOL-Gen and similar tools can be used to generate molecules also. So you can generate molecules using AI or using a physics-based method, taking into account the chemistry considerations through a software like XMOL-Gen. And then you can further assess the retrosynthetic route for your design molecules, calculate synthetic accessibility score, and apply drug-like filters to come up with a set of molecules for which you can perform the relative binding free energy calculations using a toolbox like XFAB. And then once you shortlist the molecules, you can pass it through an advent predictor to make sure that the molecule stays within parameters that are reasonable to develop drugs out of it. And then you can use a software like PatSite to analyze freedom to operate analysis. That is, the molecules that you come up with should be patentable and novel. So once you are satisfied with this criteria, then you can take them to the wet lab. The earlier medicinal chemists used to design molecules, even though they do, but to a much smaller extent, because now you can use AI to actually design molecules in the initial phase and then put it through some physics-based methods to shortlist the compounds. So once you do the medchem experiments, DMPK, animal studies, and so on, you'll be able to come up with drug candidates for taking it up for clinical trials. So now I'll briefly talk about free energy perturbation theory and what is XFEP toolbox. So Zwanzig in 1954 developed the free energy perturbation theory, by which the free energy of one system A may be related to that of a slightly different system B, and we call that as a perturbation of A going to B. In this case, A and B can be two different molecules, or it can be the same molecule in different environments. But for our purposes, we consider A and B to be different molecules in the same environment. And the difference in binding affinities between A and B can be calculated using the equation shown here, where EB minus EA refers to the difference in intermolecular potentials of the two states A and B. And here delta G refers to Gibbs free energy difference between A and B. So because of the fact that the free energies are path independent, it is possible to obtain delta G by mutating molecule A to molecule B in whichever path you choose. The delta G can be accurately calculated based on that principle. And so how does it work? The transformation of one molecule to another is accomplished by creating a series of intermediate states. And these states are not physically realistic because you cannot have a molecule that is neither A nor B, and somewhere in between. But alchemically or computationally, it is possible. And the coupling parameter is labeled lambda, and this is a parameter that controls this computational alchemical transformation between two states A and B. By varying this lambda parameter from 0 to 1, where 0 represents state A and 1 represents state B, this molecule can be converted from A to B. And utilizing the coupling parameter, what you calculate really in this case is Helmholtz free energy, which is delta A. It is represented by delta A, which represents the free energy difference under constant volume conditions, and the corresponding equations are shown here. I'm not going to go into great details about the theory part, but I just want to give you a flavor of what we are doing. And then it is important to consider the solvent in simulations. Nowadays, periodic boundary conditions are used, and these are a set of boundary conditions which are chosen for approximating and mimicking an infinite homogeneous medium. So by using this PBC, it is possible to treat very accurately the effect of water and boundary effects. Earlier, it is computationally more expensive, but in the earlier days when we didn't have super fast computers, the spherical droplet model was used to simulate protein ligand interactions. And in this case, what is done is the protein and ligand, they are encapsulated in a spherical region, and some kind of constraint is used to prevent evaporation of the water. But this method is less accurate. So how can FPP method be used to calculate relative binding free energy of a ligand to the target? It is shown in the form of equations in this particular slide, where A and B represent two different molecules. A prime and B prime represent the same molecules in the form of a complex, and the green arrows represent the physical biological transformations of ligand A going from physiological medium to the state A prime where it is complex with the protein, and similarly the case with B to B prime. And as I mentioned earlier, it is very difficult to simulate the binding of the ligand 1 to the protein because it involves the movement of the molecule, the ligand 1, to the protein complex phase from aqueous phase, let us say. Whereas the red arrows are the alchemical transformations which are easier to compute, which are easier to calculate. And here in this case, what it means is you take the molecule ligand 1 in the aqueous medium and transform it to ligand 2 in the same medium. And this is represented by delta G AQ 1 to 2, shown in red arrow. Similarly, same transformation can be done in the protein complex state, going from A prime to B prime. And because, as I mentioned, the free energies are path independent, the difference in red arrows, which represents delta G bind, that is the free energy difference, relative binding free energy difference between 2 and 1. And it should be the same whether you take the difference between red arrows or whether you take the difference between green arrows. So you end up with the equation that is shown on the right hand side bottom. That is delta G B to B prime minus delta G A to A prime. So this can be calculated using the free energy perturbation method. And this is really the essence of RBFE. And it is highly useful in a couple of scenarios. One is R group changes. When you want to compute the transformations between ligands that share a common core of atoms, they are referred to as congenetic series, and they have similar binding modes. So all you need to do is to transform the R group and come up with new molecules. in this case, in this scenario, which is very common, this RBFE calculations are highly useful. Also, when there is a core transformation, that is when the ligands do not share a common core of atoms, even then it is possible to do the core hopping through this alchemical transformation, because these molecules have similar shapes and binding modes. That is, ligands that have strongly overlapped excluded volumes when bound, but lack a straightforward atom mapping to a common core. In this case also, the scenario is also very common, especially when you want to design new molecules which are novel. What you need to do is you need to use a new core. Here also it is useful. And another way of calculating free energies, which is less accurate, is known as absolute binding free energy estimations, ABFE calculations. Let us say you have one drug like dasatinib, let us say on the left-hand side I have seen. It binds to two different proteins with corresponding binding free energy differences, delta G1 bind, delta G2 bind. This can be calculated using ABFE approach, which basically is obtained by calculating delta G value for the complex. That means mutate the molecule to nothing and perform the same calculation in the solvent and take the difference. So the advantage of this method is that it is possible to compare binding affinities of a given ligand to multiple targets of interest. So in this case, let us say the example that I shown at the bottom right is you start with an initial stage where lambda is 0, and then gradually build the molecule in the empty pocket where in between it has the character of vacuum or emptiness, and also some character of the full molecule being present somewhere in between. So ultimately, it is possible to build the molecule through lambda and arrive at the molecule of choice. Now, as I mentioned, it requires a highly specialized, highly developed force field for, especially for modeling drug-like molecules which are of interest to us. And this force field is developed using quantum mechanical calculations, especially when you consider the force field parameters for over 100,000 drug-like molecules. And this data is updated every year with about 250,000 molecules. So this XFF data force field or Hamiltonian is based on amber, and it is used in XFEP. For protein part, it uses traditional amber force field. And for ligands, this XFF force field, which is now in its third incarnation, XFF3, that uses a system-specific force field refinement protocol. For treatment of water, a model known as TIP3P water is used, which has been developed for a long time in Bill Jorgensen's laboratory. For solvation, ligands and proteins, protein-ligand complex are solvated in octahedral shaped boxes. So all these details are published and they're available. So here is a comparison of how XFF force field does compared to the Schrodinger force field, which is known as OPLSA. When we looked at a number of different targets along the x-axis, how their binding affinities are predicted using XFF force field and using OPLSA force field, we find that XFF force field produces smaller deviations, which are represented in the green bars, compared to experimental values, whereas OPLSA force field is shown to have greater deviations overall. So the XFF force field has better accuracy in distinguishing bioactive and non-bioactive conformations. The same result is obtained when you consider correlation coefficients also, that is, correlation coefficient between predicted and expected values for each target. And it is seen that the red curve is above the yellow curve, and the red curve represents XFF force field, and the yellow curve represents the OPLSA force field. This force field has been used for completing more than 400 projects in collaboration with pharma and biotech. And fortunately, this force field now is available, which has been developed over a past decade for our use, both for academic as well as non-academic purposes. And here it shows XFF force field and actually Anbu will talk in detail about it. So I'll omit this part of how XFF force field actually works. Now I'll talk about a few case studies before I talk about unbinding kinetics. The case study 1 has been touched upon by Dr. Raghu, and here the company Merck used OPLSA force field and Schrodinger software to study 8 different targets, which have about 225 ligands in total. And this work has been published in 2020. At Molecular Solutions, we have taken the same database and did the analysis. For example, in the case of CDK8, the results are shown on this slide. On the left-hand side is the table that shows comparison between experimental and predicted delta G values. And the difference is shown in the first column, showing as XFAB. And it is seen that in the difference in all these cases is less than plus or minus 0.7 kilocalories per mole. We specifically made a table of 17 ligands out of 33, for which we did the calculations, whose binding affinity is accurately predicted. And on the right-hand side, you see the molecules themselves. And this is a kinase, so it has 3 binding regions: hydrophobic, hinge binding region, and solvent exposed pocket. And there are variations in all 3 regions. And as long as these changes are not human, that is size-wise, they are about the same, you're able to get very good predictions, making changes in all 3 regions. And this is an important result because it allows you to compare molecules quite accurately in terms of binding affinities. And this slide shows the comparison of XFAB and Schrodinger FAB compared to, for 8 targets, and all the data is shown here. See, the blue boxes show the XFAB results, and the gray box shows for the Schrodinger FEP results. And overall, XFAB calculations give better, more accurate values than OPLSA values. And here you can see that out of 225 ligands, XFAB predicted very correctly within plus or minus 0.7 kilocalories per mole, which is within the range of experimental error. For 124 molecules, that is about half the molecules are correctly predicted using XFAB, whereas 109 molecules are predicted using, well predicted using OPLSA force field. And actually to do this study, we divided the data into 3 bins. That is highly accurate predictions, which are less than 0.7 kilocalories per mole, moderately accurate predictions, which are within 0.7 to 1.5 kilocalories per mole, and outliers, which have greater than 1.5 kilocalories per mole. So overall, you will see a better agreement, which is when shown in the form of histogram plot, it is very clear. For XFAB, it is better. Now, the same data is shown here in the form of scatter plots for XFAB results. And if the calculations are exactly correct, then you see all the points lie along the diagonal, where x-axis is experimental delta G and y-axis shows predicted delta G. In all these cases, the agreement is pretty good except for TNSK2, which shows poor agreement. Why is that? This is because in the X-ray structure that was used by Merck, there was a sulfate anion that disturbs the conformation of lysine 1067, which in turn affects the conformation of the ligand. And so we don't get the accurate results. Whereas we verified that by choosing a PDB without the sulfate anion, we get dramatically improved XFAB results. And this is a case study, second case study for discovery of non-covalent GPX4 inhibitors. And the challenge is that in the case of GPX4, it is a shallow flat binding pocket, and it is difficult to come up with non-covalent small molecule inhibitors. So, so a company wanted this, and by collaborating with this company and leveraging Xtalpy's generative AI for generating molecules and proprietary automation platform, to discover non-covalent inhibitors, it was possible within 28 days to deliver 3 non-covalent GPX4 small molecule inhibitors, which have IC50 better than 10 micromolar. And the timeline for the discovery is shown here. That is, the feasibility assessment took 5 days, and pharmacophore prediction using XFAB software took about 7 days, including the prediction of binding affinities. And corresponding focus library design and automated synthesis took 2 weeks to get the molecules made. And then within 2 days, in-house in vitro assay has been completed, and the result is shown on the bottom right-hand side. Since the data is proprietary, the molecules themselves are not shown, but it is enough to say that 3 non-covalent inhibitors have been discovered using this approach, Xt 17, 18, and 34, and they have IC50 values less than 10 micromolar. And the workflow is shown on the top left, on the bottom left. So you start with 10,000 molecule scaffold library using generative AI, and then you identify key pharmacophores predicted by high throughput FEP calculations, and using the data, 8,000 molecules are enumerated featuring these particular pharmacophores and taking into account the synthesizability of the molecules, and out of which 115 molecules have been suggested for synthesis, out of which 124 analogs have been synthesized by automation technologies, and that's what led to 3 potent and novel hits. So actually, there are a number of other case studies. I will skip most of those case studies because of the time requirement, but let me show you a couple of other case studies that perhaps will be more interesting. And in this case, GLP-1 agonist. This case study, is about designing novel molecules for as GLP-1 agonists, which have implications in treatment of diabetes 2, type 2 diabetes. There is a clinical candidate known as danuglipron, which was recently withdrawn from clinical trials. And the problem was that it has undesirable erg inhibition, lower activity than endogenous GLP-1, and a short action time. So this molecule is shown on the top left. This is from published literature. You can see that this is a piperidine ring, and this piperidine ring has to be replaced with different core groups to alter the properties of the molecule. So danuglipron, as I mentioned, is a representative small molecule agonist, which showed positive results. So the approach that we have taken is to replace that piperidine ring in danuglipron. It is, of course, done purely as a exploratory project, and that is, it is not actually submitted for clinical trials or anything like that. But you will see that when piperidine ring is replaced by one of the 20 groups that are shown on the right-hand side, then the experimental data is available through a publication. So when we plotted the FEP results against experimental data, you see a pretty good correlation of R square equals 0.78. So this case study demonstrates that you can use this methodology to change the core to alter the properties of the molecule. And this case study involves the drug dasatinib binding to multiple targets. This is the last study I'm going to talk about. Dasatinib is used to treat Philadelphia chromosome positive chronic myeloid leukemia. And dasatinib is a potent inhibitor of BCR-ABL, which is a tyrosine kinase involved in CML. Unfortunately, it binds to other SRC family kinases as well as other kinases such as c-KIT, FR2, etc. And fortunately, extra structures are available in the protein data bank binding to 6 different protein targets, which are shown on the right-hand side. The binding modes are slightly different. Interactions are slightly different. So, is it possible to accurately predict the binding affinity of dasatinib using absolute binding free energy estimates as it binds to multiple targets? That is the project. And this case study was carried out at Molecular Solutions and compared to a literature publication. In the literature, they calculated there are 2 ways. They used 2 ways of calculating the binding affinities. One is using density functional theory, and second is using Cham-Guyi to obtain FEP results. You will see on the left-hand side, the experimental values are shown in green squares, where the x-axis represents the 6 different extra structures. And on the y-axis, you have the corresponding delta G values. Blue crosses represent XFEP values, and red dots represent density functional theory values, calculated interaction energies. And you see that in all these cases, the blue crosses are close to the green squares, indicating better agreement. And a similar result is shown when you compare XFEP with literature FEP results using Cham-Guyi. That is, we are able to obtain better results when we used XFEP software for absolute binding free energy estimates for this particular drug, dasatinib. So you'll be able to assess selectivity whenever you have a drug molecule which is likely to bind multiple targets, it is important to assess the selectivity aspect by doing ABFE calculations. So now I will not cover other case studies because of lack of time, but I will just mention that we could apply it to a number of different cases, like predicting activity cliffs. That is, when you make a small change in the inhibitor, if it leads to a large difference in activity, then one should be able to spot those particular cases, so that in favorable cases we can actually go ahead and make the molecule and test it out. Now what I'm going to do is I'll go through a summary of the case studies here before I describe the unbinding kinetics. The XWeb results shown here demonstrate a strong correlation with experimental IC50 values across multiple targets, with better results than competing commercial software. This result is proven in-house at Molecular Solutions in the case of 8 targets, for which the Merck team performed benchmark analysis using Schrodinger FEP methodology. XWeb applications led to development of leads for targets binding to highly flexible allosteric sites. And actually, this is very important, because protein flexibility is something that is hard to account for unless you do long dynamic simulations and do the proper averaging and so on. So the XWeb code has been optimized for efficient and reasonably fast calculations. XWeb calculations are also proved to be useful for developing hits for targets with shallow pockets, such as GPX4. And the usefulness of this approach has been shown for hit finding, lead identification and optimization, and for exploring clinical candidates. XWeb results were shown to be accurate in the treatment of natural products, macrocycles, large peptides, cyclic peptides, and peptidomimetics. More studies are in progress to enhance their usefulness in cases of PROTACs, covalent inhibitors, GPCR ligands, and metalloproteins. These case studies are in progress and some have been completed, but I could not present all of that due to lack of time. Now, I just want to make the one point that I mentioned earlier also. That is, if you use XWeb and create a database of values which are accurate, that is, when you improve the accuracy of XFF force field significantly, you get data that is approaching experimental strong correlation, that is 0.9 or better. When we are in that state, we can use the data itself directly, do the calculation, and add it to the database, and allow AI to develop a model. That way, we'll be able to do much faster. In fact, Raghu gave the example of how DFT calculations, which take a long time, can be done using AI models. And this is possible because they have a database of DFT calculations, and AI uses that database. Similar thing can be done here also. Now, switching gears, I'm going to talk about residence time predictions, which is RT. Residence time is a better predictor of functional efficacy than binding affinity in several cases. Though experimental methods are there, it is very difficult to use to rely on experimental methods to optimize the candidate drug or the molecule that you want to synthesize to take it forward. Due to sampling limitation, MD is infeasible. So this unbinding kinetics from the company known as Coffee is based on a very simple principle that residence time is proportional to exponential of beta delta E double dagger. Here, the important thing is this particular value is calculated from a number of non-equilibrium candidate unbinding pathways. That is, if you look at the bottom, let us say what you're looking at the left of the figure is the absolute minimum. Then what is the closest high energy minimum? If you identify that and the corresponding transition state, then the difference between the transition state and the absolute minimum, that gives you the unbinding pathway. That is, you know how the protein unbinding kinetics actually takes place by using this particular equation and identifying that particular pathway. So the procedure used for calculating unbinding kinetics is that you take the ligand, identify ligand escape directions, and do the calculations, simulate unbinding dynamics, that is how it escapes actually. And then you identify the transition state and find out the uh, intermolecular potential, that is what is the corresponding transition state energy. And then once you have that data available, you'll be able to correlate that with k of rate with the unbinding energy that is calculated. So this is for different proteins. And the same data and a similar analysis has been carried out for validation purposes on 6 different data sets. So for various ligands, you have different proteins here, and you can see that you get a pretty good correlation when you consider dissociation constants, pK of rates experimentally, and calculated values, on the y-axis, and you see a pretty good correlation. See, and the important thing about this is that the average simulation time it only varies from maybe a few seconds to a few minutes to a few hours. That's all. So that same data has been shown on the right hand side. That is the time taken, the average simulation time taken in seconds when we use an NVIDIA T4 GPU chip. So the point I want to emphasize is that experimental residence time correlates with unbinding kinetic score using COFFEE software. And here is the scatter plot of unbinding kinetics scored as a function of experimental RT measurements. On the left-hand side, the curve that shows that is divided into 3 regions. One region on the left-hand side where residence time is less than 1 minute, then the residence time is between 1 minute to 1 hour, and residence time when it is more than 1 hour on the right-hand side, 3 boxes. So you see that overall the correlation is not bad. Using this, it is possible to quantitate the residence time for different ligands theoretically, computationally, before experimental measurements are made. And that really helps in compound design. So in conclusion, RT is a highly useful property that can be assessed quickly based on the methods presented. COFFEE simulations accelerate the prediction of ligand residence times compared to pure MD-based techniques, which take a lot of time. Of course, the caveat is that this method of prediction is somewhat approximate. That is, you don't get high correlations, but you get moderate correlations like 0.6 to 0.7, etc. As on-demand chemical libraries are growing much faster than available computing power, it is important to develop a novel approach that enables accurate RT scoring to optimally use this ever-expanding chemical space. Otherwise, you're not going to have the time to do experimental measurements or elaborate approaches for calculating the scores. Examples presented here show that COFFEE simulation methodology provides fast, reliable predictions across a diverse range of ligand-protein complexes. With this, I conclude and open the floor for questions. Thank you very much. Before moving on, Anbu's demo. Questions, please.
Thank you, Dr. Vishwanathan. That was very comprehensive. There's one question in the chat which says, can you also tell us about multiple ligands, example, original versus side chain modified to single receptor?
Side chains modified, compounds binding to a single receptor, different compounds. Let me see the question again.
It's in the chat. Yeah, if you just click the chat button at the bottom right of your screen.
Yeah, sure. Sorry. Can you also tell us about the multiple ligands? For example, original versus. Oh, okay. That is selectivity. See, basically, it is possible to mutate the protein itself. That is, change the side chains and calculate the binding free energies for the modified proteins. This is exactly the approach used for assessing selectivity. I think that is original versus side chain modified. I think you're talking about a particular protein, but if you want to talk about R group changes for a single ligand, I showed the very first example shows R group changes. That is, For CDK8, you have you have multiple ligands binding to the same single receptor CDK8, and we got very accurate predictions. I hope you saw the case study.
Next question is, what is the significance of intermediate alchemical states?
What is the significance of intermediate alchemical states? Yeah, this is a very good question. See, that is the important thing is in the phase space, it is possible to calculate the intermolecular potentials as you mutate one molecule to another, which is determined, that is, the accuracy is only determined by the accuracy of the Hamiltonian. Theoretically, the method presented is perfect. And so the significance of the intermediate state is at any given state, let us say when lambda is 0.2, then at that state, the molecule that is being simulated has 20% character of the ligand A and 80% character of ligand B, or vice versa. That is, you can move along the intermediate states and gradually modify the molecule that is being simulated to have a partial character of A and partial character of B. So and unless it is done, you are not going to be able to calculate the free energy of the ligand when it mutates to B. And it is this whole process, the simulation, it succeeds only when the mutation takes place gradually. That's why we divide the whole range into several windows, 12, 14, whatever it is. And for each window, you simulate it for 1 picosecond or less, which is large enough to allow a good sampling and the MD calculation to go through.
Thank you so much, Dr. Viswanathan. That was